Hi, it's Ryan. Today we're going to talk about the motion of charged particles in external magnetic fields, and then we're going to discuss briefly some magnetic fields that are produced by currents. More specifically, a few produced by magnetic fields produced by a straight wire, a wire loop, and a solenoid. But as I said, we're going to start with the motion of charged particles in an external magnetic field. And before we begin, I want to just remind you, so we'll recall the motion of a charged particle in an electric field. And so we could draw our electric field lines. I'll just keep it blue. And inside of that, we'll place a charged particle. We can just call it Q. And we'll note that it's a positive charged particle. And we know a positive particle in an electric field will experience some electric force, Fe, in the direction of those field lines. And so this particle should end up displacing along the same direction as the field line. And we know that if it were a negative particle, it would do the same thing, only in the opposite direction. And you can always remember this because we determined the direction of the electric field based on how a positive test charge would be affected by the entity that's producing that electric field. Anyway, this is just a reminder. The motion of a charged particle in a B field is a little bit more complicated, but not really. Maybe I should not say complicated, I should just say different. And so what I'm going to do here is draw this out. So we have some magnetic field going into our page or screen. And I'm going to put a positive charged particle, maybe right here. And so what we can do, and I also have to tell you that that particle will have a velocity that looks something like this. V for the charge. And if we have a moving charged particle in a magnetic field, we know that it will experience a magnetic force equal to Q V cross B. So we can use right-hand rule number 1, and we can point our fingers in the direction of the velocity. And then keeping our fingers pointed at this angle, we can curl them into the page because that's the direction of the magnetic field. And if we do so, I think you should end up getting a magnetic force that looks something like this. I'll use blue maybe. So you can verify on your own that that's the direction the right-hand rule yields for the magnetic force on that particle. Notice that it's 90 degrees from the velocity vector and from the B field vector, and we know that that's always the case when we do a cross product. Because it's 90 degrees, it won't change the magnitude of that velocity, but it will create an acceleration, like so, which will change the direction of that velocity. So the speed won't change, but the direction will. So in some amount of time later, the particle may be here. The velocity vector would have been accelerated this way due to that acceleration and that external force, but it should be the same length as it was before. If we apply the right-hand rule to the new velocity direction, we'll end up getting a magnetic force that looks like this, which will cause a new acceleration that looks like this, and that will have the same sort of effect on the particle. And if you can kind of imagine doing this over and over again, what we'll show is that the particle will undergo uniform circular motion. As long as that magnetic field is constant. So I'm going to say let's play around a little. We'll use this picture. Imagining that we're singling out maybe one point. So we could draw an FBD for our charged particle, and it won't be very tricky. It looks like there's just one force that we're worried about, the magnetic force, FB. And of course, if there's an imbalanced a number of external forces, there must be an acceleration. Now we could note A in this diagram is always pointed toward the center. Of the path created by Q. That means this is a center-seeking or centripetal acceleration. So, like we would with any FBD, if we sum the forces on Q, it looks like we're only worried about one direction, the centripetal direction. And so we've got FB equals MAC. Recall from Physics 1, AC is V squared over R. And we could even show that this has some sort of radius here, R. FB is Q V cross B, but we're not working with vectors right now, so I'm going to do the absolute value sign around that, which of course in math means magnitude when we're dealing with vectors. So that will end up being QVB sine phi, where phi is the angle between V and B, but we already said earlier, and in our picture we can see that the angle between V and B is 90 degrees. B is going into the page, so any vector that's in the plane of our page will be 90 degrees or orthogonal to it. Well, the sine of 90 degrees is just 1, and so this will become QVB equals MV squared. Oh, and I messed up there. I should say R. It looks like we can divide away one of our V's. And so we might just note that this is a statement that relates. So let's write it like this. V equals QB over, QBR over M. This is the tangential, let's just say the speed of a charged particle in a uniform magnetic field. And so analyzing this and maybe some other information given, you could determine both the speed and the radius of a charged particle in any uniform magnetic field. I'm going to note one more thing. I'm going to say this quantitatively defines the motion. So conceptually speaking, we know there's a centripetal force causing a centripetal acceleration that causes this to move in uniform circular motion. But if you needed to quantify any of that, this is the trick. Okay, so we're going to shift gears just a little bit. And we're going to look at the magnetic fields produced by currents in specific shapes, namely 3. So as I said, with the first geometry or shape that we're going to look at is just a long straight wire. And a long straight wire might look something like this. And we can draw a current in that wire that's going from left to right. And now we can figure out what magnetic field direction this wire produces using something called the second right-hand rule, or right-hand rule number 2. But I'm just going to draw it in for now, and we can talk about the second right-hand rule soon. So this will produce a magnetic field that's coming out of the page above the wire and going into the page below the wire. And so if you can kind of imagine, we're looking at a 2-dimensional representation of something that's actually coming in and out of the page, creating closed loops. So keep in mind, if it's coming out of the page here, looping around, going into the page there, and we would get a looping magnetic field then that looks something like that. And the closer you are to the wire, the stronger that magnetic field's magnitude would be. And we could use something called Ampere's law to derive the formulas I'm going to give you, but we don't have time this semester to work through that. So I'm going to say mathematically. So anytime you're working with a long straight wire, you can determine the magnitude of the B field using this equation. And I'm even going to show here that if we're looking at a point P, then this distance is R. And so we'll define this for you. We'll say where B is, of course, the magnetic field. And maybe we should say the magnitude. We get the direction from the second right-hand rule. We have current. We have the distance from the wire. Mu sub O is a constant of our universe called the permeability of free space. It basically is a constant that helps us predict how magnetic fields propagate through a vacuum, and it's 4 pi times 10 to the negative 7 newtons per amp squared. And so anytime you need to determine the magnitude of a magnetic field produced by a current-carrying wire, you can use that equation. The second right-hand rule is a little bit easier than the first right-hand rule. All you really do is take your right hand, point your thumb in the direction of the current, and your fingers will wrap around the wire the same way that the magnetic field does. So you can even try that in this picture to verify how that works. If you just give me a thumbs up with your right hand, but then turn your thumb so it points in the direction of I. You can even take your pencil and put it inside of your palm so it's pointed in the direction of I. And then you can imagine that's the wire. And as your fingers wrap around the pencil, that would be the magnetic field wrapping around the wire. Next, we're going to look at the current, the B field produced by a current-carrying loop. So if we take that wire and we just turn it into a loop, it will produce a slightly different magnetic field. So I'm going to just take that wire and turn it into a loop. And I'm going to give the current the same sort of direction it had up there. And now if you take your thumb and you point it in the direction of the current on this side, you can see that your fingers would have to go into the paper here and would wrap around the loop and come out of the page there. So I'm going to draw dots on the inside of this, and you can really take your thumb and go in any direction in that direction along the circle, and you'll see that no matter where you are, that's what happens. We'll end up with this nice uniform field inside the loop, mostly uniform, and it will produce X's outside of itself. But often we use current loops to produce uniform magnetic fields for experiments and other things, or motors, or a lot of other applications. Anyway, that is the magnetic field produced by a current-carrying wire that's been turned into a loop, or any loop that's carrying current for that matter. Mathematically, which is of course what everyone's waiting for, the magnetic field for a loop is mu sub O I over 2r, and I could note in here that r is the radius of our loop. And so I'm not going to define everything again. It's all been defined for you above. Maybe r is the radius this time. And I'm going to note one more thing for this. If you have multiple loops, it just is proportional. It increases proportionally with the number of loops. So our equation looks almost the same. We know that we could get it for the multiple loops just by adding an n for the number of loops in our numerator. Something else that's kind of interesting is that the equation for the line and the equation for the wire differ only by a small factor. I wonder if you could figure out that factor. Anyway, last but not least, we have something called a solenoid. So now a solenoid is something that takes multiple loops, like hundreds or thousands of loops of wire, and because there's so many, we don't just stack them on one another. We create sort of a tube of loops, usually around some sort of not conductive material, Also, it's important maybe to note to yourself that when we create solenoids or loops of wire, we need to have them insulated from one another, or else they'll just act like a single conductive body. So a solenoid will have some sort of length, L. Sorry for my artistic inabilities. And of course, it will have some radius for the circular face. And again, we could use Ampere's law to determine these equations, but I'm just going to give them to you. We'll say mathematically, the magnetic field for a solenoid is mu sub O little n I. And we'll note that this is the same as saying mu sub O big N I over L. So n is the linear number density of turns. So if you run into, I don't know, a homework problem that uses any of these shapes and ask you about the magnetic field, you know more than you originally thought. Hope you had a wonderful time listening and have a wonderful day.